All right, everyone. We have our unit test tomorrow. We had a little bit of homework over the weekend, worksheet number 9. Let's take a look at the answers to worksheet number 9. Any issues with any of those questions here, Patrick? 4 and 7, okay. 2, okay. Max? 1 or 3? You know what, guys, I'll tell you what. We did this stuff on Friday, right? Sorry, on Thursday, right? So this stuff, you're looking at this stuff for homework for the first time, and sometimes it's a little bit confusing when you do it for the first time. A lot of these questions are real similar to each other, so pretty sure we don't have to go over all of these questions. Okay, we're going to pick, what I'll do is go through the worksheet, and I'll pick a few questions that I think are pretty representative, and I think that should clear up the issues that we have with the rest of them as well. If it doesn't, then we'll deal with that, okay? But if it does, then we won't bother going over 7 questions. We'll go over 2 or 3 questions. And if we can accomplish the same thing with that, then that's exactly what we'll do. If you remember when we did this on Thursday, this whole idea of conservation of energy, this whole idea of charges accelerating in electric fields, we saw them as if they were cars going up or down hills. Okay, I want you to remember this very clearly for tomorrow's unit test. If a charged particle speeds up, then we should treat it like a car going down a hill. If a charged particle slows down, we should treat it like a car going up the hill. If a charged particle is speeding up and it's going down the hill, then we would say EI is equal to EF, and we would say it's a conversion of potential to kinetic energy. In other words, it would be mgh is equal to 1/2 mv squared, assuming that is, it started at rest and it finished with no final height, right? If a charged particle is slowing down, like a car going up a hill, it would be something like this. 1/2 mv squared is equal to mgh. Now again, assuming that it started at a height of 0 and it ended with no speed, right? It ended with just potential energy. Now what we're going to do though when we're talking about charged particles is simply replace the mgh, whoops, not the 1/2 mv squared, let's replace the mgh with the electric potential energy. So if the car has a height and therefore has an initial gravitational potential energy, then the charge has a potential difference and therefore has an initial electric potential energy. If at the end of the problem the car has gone completely down the hill and only is moving, and therefore has no gravitational potential energy, then the charge, after it's gone across the potential difference, would only have kinetic energy as well. And it wouldn't have electric potential energy at that point. Okay, let's take a look at let's say question number 3 here, first of all. Okay, question number 3 on the worksheet. And question number 3 on the worksheet says an electron is accelerated through a potential difference of 9 volts. The electron begins at a speed of 6.0 times 10 to the 4 meters per second. What's the final speed of the electron? So we do have a charge here. We have a mass of the electron as well. I'm not going to write those numbers down simply because I know what they are. They're on my data sheet. I'm just going to save myself a little bit of time but just by writing Q and M to remind me that I have those numbers if I need them. I have the initial speed. The initial speed of this electron is 6.00 times 10 to the 4 meters per second. I have the initial potential, or do I have the initial potential? It tells me that I have a potential difference of 9 volts. What is that exactly saying to me? A potential difference of 9 volts. Listen, do we know what the initial potential is when I say the potential difference is 9 volts? Do we know what the initial height is if I say a rock falls 30 meters? Do we? What is it? 30 meters? Is it for sure? Not necessarily. It could have been 80 meters. But if it was 80 meters, then what's the final height? 50 meters, right? Okay, we have the potential difference here of 9 volts. What's the initial potential? Well, we don't really know, do we? It could be 9 volts, the final could be 0. It could be 18, the final could be 9. It could be 109, and the final could be 100, right? Do we really know? We don't. But we can define, for a conservation of energy problem, a 0 potential energy wherever we want. So it makes sense probably to define the 0 potential energy at the end of the problem. If that's the case, if we define the final potential as 0 volts, then the initial potential would be what? 9 volts. that make sense? So if I drop the rock from a height of 80 meters, if I drop it over a height difference of 30 meters, and the initial is 80 and the final is 50, okay, I can say HI is 80 and HF is 50. That's fine. But I can also define the end point as my 0 point and say the final is 0 and the initial is 30, even though that's not really what it is relative to the ground. Okay, it's all relative, right? If I define my initial potential relative to my final, and I say my final is 0, then my initial would be 9.0 volts. Does that make sense, guys? Okay, so even if you don't have the exact number, that's okay. If you define the end as 0 potential and the initial relative to that, then you're okay. All right, what else do we have here? We're looking for the final speed here. We're looking for VF. Okay, that's a lowercase v instead of an uppercase v. We're going to say EI is equal to EF, just like a car going, which way is it going? Up the hill or down the hill? Charged particle speeding up here, isn't it? It's charged particle, or sorry, the car is going down the hill. So we would start off with potential energy because it's got a height. We would also start off with kinetic energy because it's moving at the top of the hill. And at the bottom of the hill, it's got simply kinetic energy. And of course, we're going to replace MGH with QVI. And I told you, you don't need to even write down MGH if you don't want to. I do, okay, just to illustrate the similarity with the problems that you did last year. Okay, but if you recognize that already and you just want to go straight to this step, then that's okay. Okay, we've got our numbers here, 1.6 times 10 to the minus 19 for the charge. It's negative, but we always drop the sign of the charge. VI is 9 volts. The mass is on our data sheet as well. And VI is 6 times 10 to the 4. Don't forget to square this. Lots of times people forget to square V in kinetic energy, but especially when V has an exponent already. People seem to forget to square it. The mass here is 9.11 again. Solve for V. Let's pull out the calculator and solve this one as a group here, okay? We're going to solve the left side first. We're going to say 1.6 times 10 to the minus 19. Listen, when you're doing exponents, don't do the 1.6 times 10 to the negative 19. Don't do that. Okay? Don't. I see that so many times. Don't do that. Most times that will work for you. In fact, every time it will work for you if you use brackets in the proper place. Okay, but this is the way that your calculator was designed to deal with exponents. Okay, times 10 to the whatever, deal with scientific notation. So do it that way. 1.6 times 10 to the minus 19 times 9 volts. Okay, let's press equals. Now let's add to that, use some brackets here. 0.5 times 9.11 times 10 to the minus 31. Times, let's use some more brackets here because we've got a square. 6 times 10 to the 4. End bracket that, square it. End bracket that. Okay, that's my left side. Let's multiply it by 2 to get rid of the half. Let's divide it by 9.11 times 10 to the minus 31. And then what do? Listen, if this is a multiple choice answer question, guarantee you that option's there, right there. But how do you know that's wrong? Well, that's right, because we didn't square root it. But if I just see 4 options, and I see that answer as an option, how do I know that that's the wrong answer? It's too fast. It's faster than 3 times 10 to the 8 meters per second, right? A typical speed for a charged particle, not always, but a typical speed will be in that 10 to the 5, 10 to the 6 range. If you see an answer that's 10 to the 10, 10 to the 11, 10 to the 12, okay, I can almost guarantee you that if you square root that option, it's the answer. Okay, because they're going to give you the square of the answer in a case like this, okay, which is going to be somewhere in the 10 to the 10, 10 to the 11, 10 to the 12 range. Okay, let's square root that. We end up with 1.78. 1.78 times 10 to the, what was it, 6? 1.78 times 10 to the 6. Does that question make sense? Listen, I think if you're okay with a question like number 3, I don't think there's going to be any issue with a question like number 1 or number 2, right? Okay. Number 4, real similar to number 2 where you asked for the potential difference. Let's take a look at question number 4 here, okay? Just because you're, not because it's harder, but just because you asked for a different variable in question number 4. This is a proton. Okay, we know what the charge and the mass of the proton is. Be careful though. Yeah, I'm going to write that down and circle it just to remind me that it's not an electron. Okay, one of the common mistakes is, since we use electron data so often, is to just go to that right away, right? And the charge will be the same, but the mass will be dramatically different. So if you use, listen, if you use the charge and the mass of the electron in this question and it's multiple choice, that option's probably going to be there as well because it's such a common mistake. It's a proton. We know the data, we just look it up on our data sheet. It accelerates from a speed, an initial speed of 5.00 times 10 to the 4 meters per second, to a final speed, VF, of 5.00 times 10 to the 6 meters per second. So it's speeding up, right? Charged particle is speeding up. It's gone up by a factor of 100. That's like a car going down a hill. We want to find the potential difference required to do this. We want to find delta V here. Car goes down a hill. But the car at the top of the hill is moving. So what kind of energy does it have at the top of the hill? It has kinetic and potential energy. We'd say if it's a car, mghi plus 1/2 mv squared equals, what kind does it have at the bottom of the hill? It's got kinetic energy because it's moving, right? Now, of course, we're not dealing with the car, we're dealing with a charged particle, so we're going to replace mgh with qv. It's easy for me to erase that right on this board. Okay, it's a little bit messier for you to erase that yourselves. So again, if you want to go straight to this step, that's okay. But think of it as the car going down the hill. All right, let's write in some numbers here. 1.6 times 10 to the minus 19. We don't know what VI is. Okay, that's not initial speed. That's initial potential. The mass is 1.67 times 10 to the minus 27 for the mass of a proton. That should be VI, right? Times 5 times 10 to the 4 squared. So we're solving for VI here. What are we looking for? It's not the initial potential. We're looking for the potential difference. But what are we doing here? Like, how are we solving for the potential difference if I'm really, how are we going to find the potential difference if I'm really solving for the initial potential here? What did I, in effect, do? Huh? I assumed the final potential was equal to 0. That's what I defined it as, right? As 0. Do we know that it's 0? No. It could be 50. Okay? But it doesn't matter. If I define it as 0, and I can define 0 potential wherever I want, just like the height I can define as 0 wherever I want, then my initial potential would be the same as the potential difference. So that's where I want to go with that, right? Okay, let's calculate this one as a group here now. Let's get the right-hand side. We're doing the right-hand side here, 0.5 times 1.67 times 10 to the minus 27 times, let's do some brackets here, 5 times 10 to the 6. Square that. Okay, let's subtract from that, because we're taking the other one over to the other side by subtraction. 0.5 times 1.67 times 10 to the minus 27 times, let's do some more brackets here, 5 times 10 to the 4, and the bracket. Okay, now let's divide it by 1.6 times 10 to the minus 19. And we get 1.30 times 10 to the 5. So the initial potential is 1.30 times 10 to the 5. The final potential, well, if we define it as 0, then that initial potential would be the potential difference. What if we had to define our final potential as 1 times 10 to the 5? If, for whatever reason, we had to define our final potential as 1 times 10 to the 5. Could we have done that? Sure we could have. We could have defined it as whatever we wanted. Probably wouldn't make sense to do that, but we could have. What would we have gotten our initial potential to be if we defined our final as 1 times 10 to the 5, Travis? Yeah, 2.3 times 10 to the 5 is what we would have got our initial potential to be, right? And our potential difference would still be the difference between the two, 1.3 times 10 to the 5. That making some sense? Yes? Okay, I do definitely want to take a look at question number 5 here. I knew that would be one that we'd have to go over here. A number of people asked me questions about that already on Thursday. It says a potential difference of 100 volts exists across two parallel plates that are 16 centimeters apart. I'm going to draw a picture for this one. 16 centimeters apart, we got a potential difference of 100 volts that acts between those two plates. How fast is the electron moving when it's traveled 4 centimeters, when it's traveled 8 centimeters, when it's traveled 16 centimeters? I'm going to do question A here. Okay, listen, I think if you can do question A, you can do the rest of them as well. This is a charged particle speeding up. It's like a car going down the hill. It begins at rest, so there's no kinetic energy at the beginning. It's got to have potential. Well, we're going to write in QV. It's a car at the top of the hill, okay, MGH, or electron ready to speed up going down the hill, QV. When it's traveled 4 centimeters, okay, it's still moving. It's still moving. It's like a 100-meter high hill. The car's gone down 25 meters, right? It's gone a quarter of the way across. What kind of energy does it have at this point? What kind of energy would the car have before it's reached the bottom of the hill? It'd have kinetic and potential. We'd say 1/2 mv squared plus potential mgh, or in this case, potential qvf. All right, we're talking about an electron, so it's 1.6 times 10 to the minus 19. What would the initial potential be there? Sorry? Nope. The initial potential would be not 25, no? Okay, hold on. We'll go back to that. You can do it that way, yes. But we'll do it 2 ways here, okay? That's probably not the most obvious way, but it actually is a little bit quicker, so we'll take a look at that. Anybody else what the initial potential is? Okay, initial potential is 100, good. The mass of the electron is 9.11 times 10 to the minus 31. Vf squared, that's what we're trying to find. What's the final potential here? 75. Listen, the 4 centimeters has nothing to do with it other than telling us that we've gone a quarter of the way across the potential difference. Therefore, if we started with 100, we've lost a quarter, right? So we're left with 3/4. Okay, when we do the math on that and solve for Vf, we end up getting 2.96 times 10 to the 6 meters per second. Now, Paige made a good point there just a minute ago. She said the initial potential was 25. What's she doing? She's setting what? Yeah, she's setting Vf equal to 0. Okay, we told you can define zero potential as anywhere you want, right? And she's defining the 0 potential as right there. Well, if that's 0 potential, then there is no potential energy at the end of the problem, right? Because you're at the bottom of the hill. But then Vi would only be 25 volts, because that's where you started if that's 0. Matt?
Is that the only way to get energy at a specific moment between the two plates? Like with a ratio like that, or is there an equation?
To find potential energy?
Because I'm just wondering what if we had like a number that was 4, 8, or 16 that was like 7 points.
Oh, okay. Yeah, that is the only way. Yeah. To be honest, the question, guys, if you didn't hear that from Matt, was, is that the only way to find the potential there? The initial and final potential is to do kind of a ratio. Say, like, look, 4 centimeters is 1/4 of 16 centimeters. He said, well, what if you get, like, it's not 4 centimeters, it's 7.38 centimeters. It's gone across instead of 4 centimeters, right? It's still the only way to do it. Okay, but it's just going to be, it's not harder, it's just going to be a little bit not as pretty mathematically, because you're going to end up with a decimal number for V, right? To be honest, I don't expect you'd encounter something like that, because they're not usually trying to trick you and to test, crazy mathematics. They're just trying to usually see if you understand the concept. Okay, and if you understand the concept in this question, And you understand the concept just as well with if it's 7.38, right? It just isn't quite as pretty mathematically. So I'd be surprised, but you never know. Okay? If you do end up something like that, then that's exactly the way you do it still. Okay. Okay, B and C go exactly the same way, guys, except of course our initial and our final potential is a little bit different here. Finally, let's take a look at number 7 here.
I
Yep.
also had like a totally different way that I did this one.
Okay.
Right, so I
Yep.
had electric field, but it simplified it.
Okay.
And then set that
Oh, I think I'm liking this already, Matt. Actually, I think I'm liking this method already here. I think I know where you're going with this, but I want to hear you out here. So Matt found the electric field strength. Okay, and that's going to be 100 volts divided by, what are we going to use here? 16, 4, 8? Yeah, we got to use the distance between the plates, right? Okay, it doesn't matter how far it's traveled. It's going to be 0.16 meters. What'd you get for that, Matt?
625.
Okay, 625 volts per meter. Okay, I didn't calculate that number. Okay, but that's still an absolutely correct number, right? I just didn't need it the way that I did it. Go ahead.
And then I set that equal to the electric field experience.
Okay.
It
Yeah.
over 1.6 meters back.
Yeah, and then you solve for force.
1 times negative 16. And so that was equal to mass and acceleration.
Okay,
So I solved for acceleration.
it's not exactly the way that I thought you were going to go with this, but it's still right. Okay, so solve for acceleration. What'd you get?
I got 1.09769 times 10 to the 14 meters per second squared. And I just used the square root of acceleration times distance.
This one.
And
Okay. Good. Good. I like that. I like that. No, but here's the thing. No, Matt, I'll tell you what, that's not the way that occurred to me, to be honest, at all for solving that question. But the reason I like that is because even though that's not the way that occurred to me for this question, that's exactly what I do when I come across a question that stumps me, is I try things, right? But I don't try random things. Hey, Matt found electric field strength. Hey, that was completely irrelevant for the method that I used, but it's not wrong, right? There's parallel plates. There is an electric field strength between them, okay? So we found the electric field strength, okay? And then he used that to find the force. That's a perfectly valid electric field strength, a perfectly valid force. The worst that's going to happen if he starts using that method is he gets to force and says, oh, it's not helpful to me. I got to start again. That's the absolute worst that's going to happen, right? Best it's going to happen, he's not sure how to do this question. He's got electric force. Hey, wait, I can get something else from that and eventually get the right answer, okay? The point that I'm trying to make there is that, listen, if you don't know what you're doing, I'm glad you didn't know what you're doing on the mat, because it illustrates a great point. If you don't know what you're doing, just keep trying things, as long as they're valid things, as long as you're finding things that aren't like, completely irrelevant concepts, right? V is equal to F times lambda, the wave equation from physics 20, right? Isn't relevant here, right? But you're doing relevant things. It's funny how sooner or later, the answer sometimes just comes through, even when you don't know exactly where you're going with it as you're doing it. Yeah. Yeah, sure. Yeah, because the acceleration is going to be the same in B and C, right? You've just got a different displacement now. So then at that point, the displacement isn't irrelevant anymore like it was for me, right? Does that make sense, guys? Matt, funny enough, actually, this equation right there, although you might not realize it, that really is conservation of energy. Okay, it comes from the law of conservation of energy. If we're dealing with a hill, we say EI is equal to EF, and we say that it's got an initial speed here of whatever, okay, VI. We'd say in this case, 1/2 MVI squared plus MGH, right, equals the bottom of the hill, 1/2 MVF squared, right? Okay, let's multiply every term by 2. Cancel out the mass. We're left with VI squared equal plus GH equals VF squared, right? VF squared is equal to VI squared plus Whoops, forgot to multiply that by 2, right? Plus 2 times GH. GH is A and D, right? Okay, so that's absolutely conservation of energy when we're talking about the car going down the hill. But since you've introduced for the acceleration, not G, but you've got the acceleration from this, still ends up being conservation of energy. It's just it's sometimes not obvious that that's what you're doing. Okay, any questions on that? Either of the methods? Okay, let's take a quick look at number 7 here. And then I think that should take care of it for this concept here. It says, an electron enters the gap between parallel plates with a potential difference of 20 volts, 10 centimeters apart. At this speed, it's moving from the negative plate to the positive plate. Okay, that's going to speed up. I don't want to do 6A. We've done a number of those questions already, when the charged particle is speeding up. I want to do the second part of the question, when it's moving from the positive plate to the negative plate. What's going to happen if a negatively charged particle is moving at a certain speed at the positive plate? What's going to happen to it? No. It's moving toward the negative plate. It's not going to get pushed faster. It's going to slow down, right? Yeah. So it's going to slow down like the car going up the hill. Well, if the car is going up the hill, it's going to have kinetic energy to start off, and it's going to have potential energy when it reaches the top of the hill. And we're looking for the speed at the top of the hill, so it's also going to have kinetic energy. But we're going to replace the MGH with QV. Okay, so now let's say it's an electron, 9.11 times 10 to the minus 31. Starts at a speed of 6 times 10 to the 6. Don't forget to square that. The potential difference is 20 volts. And we're solving for VF there. So what's our energy conversion taking place here? We start off with all kinetic at the bottom of the hill. As it goes up the hill, kinetic is converted to potential, right? We still have some kinetic left. We haven't converted all of it, but we've converted some of it. You guys feel okay about those? All right. We're going to give you, it's 9:30 here. I'm not going to start the new unit today. I'm going to give you a quick little outline of the test tomorrow with just the topics that we've covered. We'll talk about a few of those things kind of as we go. I've got a couple of multiple choice questions that I'd like to do if hopefully we can get to those questions. And maybe I'll even pull out a copy of the test and give you a couple little hints about what you might see on the test for tomorrow, okay? Do what you need to do here, guys. If you want to copy this down, great. If you want to just literally snap a picture of it, okay, that's fine too. If you want to go back and watch the podcast tonight and have a look at that, that's okay too. We started off the unit here a few weeks ago talking about electric charge, the types of charge, the positive and negative, where they come from, the origin of the charge, right? We're talking about positive charge coming from having not just protons, but more protons than electrons, okay, and so on. The units for charge, we talk about the coulomb as a unit of charge, but we often see something like a microcoulomb or a millicoulomb or a nanocoulomb, okay? Be able to convert all of those to coulombs, because when we're doing a calculation, we know that we have to use coulombs and not microcoulombs or whatever, okay? By the way, this is 10 to the minus 6. This is 10 to the minus 3, and this is 10 to the minus 9. But those are on your data sheet. Okay, those conversions are all on your data sheet. Just be prepared to use them. Know how to find the charge of the electron, the proton, even an alpha particle, which we don't even really know what an alpha particle is right now. But anything that's on your data sheet, know how to find it. Know how to find the charge of it. Okay, on our data sheet, it'll say something like for an alpha particle, the charge is 2e. But of course, we know what that means, right? 2 times the elementary charge. 2 times 1.6 times 10 to the minus 19 coulombs, giving me 3.2 times 10 to the minus 19 coulombs. We also found the number of electrons. Okay, we talked about this back near the beginning of the unit. We want to find a number of anything, Travis. We want to find a number of anything in physics 30. Okay, let's get the total for something, and then the amount for one, and let's divide the two. Okay, you want to find out the total number of oranges in the bag. Yeah, I got a bag of oranges. Each orange weighs 250 grams. Okay, my bag of oranges weighs 750 grams. How do I find how many oranges I have in the bag? I'll take the total mass and divide it by the mass of one orange, right? Gives me 3 oranges. The total number of electrons is the total charge divided by the charge of 1 electron. And that should give me the number of electrons. And then finally, in our first little blip there, or first little thing here, we talked about the electroscope. An electroscope measures the presence or absence of charge. It doesn't tell me whether we have negative charge or positive charge. It doesn't tell me how much charge we have. It just tells me whether I have charge or not. And again, if we see the electroscope leaves spreading apart, then we know that we have charge there. We talked about conductors and insulators, Tanner. A conductor is a material that has electrons on the outermost levels, not so tightly bound to the nucleus. They're pretty free to move about, right? An insulator is exactly the opposite. The electrons are more tightly bound to the nucleus. Give me an example of a good conductor. Yeah, I mean, in general, metals, right? Silver is a great conductor. Gold is a fantastic conductor. Copper is a good conductor. Aluminum is a good conductor. Basically, all metals, right? Give me an example of a poor conductor. Wood is a very poor conductor. Okay, wood is a poor conductor. It is a good insulator. So poor conductors are good insulators and vice versa. These diagrams you certainly don't need to copy over because we talked about these when we went through the unit. I just put these in there, not necessarily to even explain them again, but to remind you of what these have to do with, okay? To remind you really of what charging means. Okay, we charge by conduction and we charge by, sorry, I missed the first little thing there. I kind of skipped past it. We talked about those 3 laws, right? Those 3 laws: opposite charges attract, like charges repel, and charged objects attract neutral objects. Protons don't attract neutrons electrically, okay? Because the neutron isn't a neutral object. It's just a neutral charge. Okay, we have to have charged objects attracting neutral objects so that we can get that separation of charge. And we talked about the law of conservation of charge. Conservation of charge says charge can't be created, can't be destroyed. So when you touch 2 things together, they're going to try to balance each other out, right? We'll assume that they do always balance each other. When positive touches neutral, okay, they both become positive. Okay, when negative touches neutral, they both become negative, and so on. And these diagrams that you see down here really should go with the next page, because the next page is what talks about charging objects by conduction and by induction. Okay, you guys know the deal here, right? Okay, real quickly, we got neutral dust particles in the air. As those neutral dust particles go through here and they touch these negatively charged rods here, what happens to these neutral dust particles? Negative touches neutral, they both become negative. So the dust particles become negative. As the negative dust particles now go through these positive plates, what happens? They get attracted to it, right? So we get charging by what when the neutral dust particles touch the negative rods? Charging by, sorry? Conduction, yeah, because there's a transfer of charge from the rods to the dust particles. Right? Negatives always transfer from the rod to the dust particles. That's conduction, more specifically charging by contact. As these negative particles go in between these plates, they're attracted to these positive plates. And of course, when they touch these positive plates, okay, they're going to stay there, right? So the air particles now are going through there, minus the dust particles, minus those charged dust particles. Would we have gotten some of those neutral dust particles being attracted to these positive plates? Sure, charging by induction, right? Neutral particles would be attracted by that separation of charge. But we're going to get more if they're negatively charged first. So we talked about charging by conduction, friction and contact. When we rub two things together, okay, we transfer charge from one to the other, electrons from one to the other. Okay, when we touch two things together or bring them close enough, the charges will just jump, then that's charging by contact. Bottom line is conduction always involves a charge transfer. Induction, we talked about the temporary separation of charge and the permanent charge. How do we introduce that permanent charge? How do we make the temporary separation of charge permanent? Yeah, we ground it, right? But it doesn't physically have to be a wire attaching it to the ground. It could be some other fairly big object that will basically serve as the ground. I think we had a quiz question on that, didn't we? Where we had charging by induction permanently, but it wasn't physically a ground wire that was causing it to happen. It was just another ball being brought nearby that was causing it to happen. Okay, that other ball basically served as the earth and took away the electrons or added the electrons, whatever the case was in that situation. Bottom line is, if the thing doing the charging, if the thing that's causing all of this to happen isn't transferring charge, then we still call it induction, even if there is charge being transferred from one object to the other within that. And then, of course, our applications of charging by conduction and induction. We talked about a couple through the unit. Okay, we also talked about lightning. Okay, we did that one. Early on, we did a couple of multiple choice questions with that. We got a thundercloud that has a negative charge on the bottom. Okay, what's going to happen to the Earth here? Before lightning strikes, well, let's say before lightning strikes. Before lightning strikes, this hasn't happened yet. Okay? The Earth is neutral at the surface, right? What's going to happen to the surface? Sorry? Good. Yeah, it's going to become positive by induction. The electrons get pushed away. They go down here somewhere, and it becomes positive by induction before it strikes. Now, that's charging by induction, right? It's a temporary separation of charge. We can just ask the question, though, would that be conduction? Would it be conduction? Not that part of it, but when the lightning actually strikes, now you're getting a whole bunch of electrons going down through there, transferring to the Earth. That would be conduction. More specifically, it'd be charging by contact, even though the cloud isn't actually contacting the Earth. Right? We talked about the torsion balance experiment. Basically, remember you had this rod that hangs from the ceiling. Okay, charge 1, charge 2, you bring in nearby. Number 1 is going to attract or repel charge 2. The string is going to twist. The amount of twisting on the string tells us how much force was present. We can measure charge 1. We can measure charge 2. We can measure the distance that separate the two. And we can measure F. We do 3 experiments. The first one, manipulate Q1. What do we keep the same, by the way, when we manipulate Q1? Q2 and R. That's a linear relationship. Change Q2 now. Let's keep Q1 and R the same. Linear relationship. F versus R. What's that shape look like? Yeah, it's an inverse square relationship. By the way, we're keeping Q1 and Q2 the same in this experiment. Okay, it provides an inverse square relationship. F is related to Q1, F is related to Q2, F is related to the inverse of the square of the distance. Put them all together, and we get F is equal to a constant times all of that stuff. And that's Coulomb's law. And then, of course, we talked about Coulomb's law. Easy enough to find the force between two charges. What about when we have three charges? Okay, what about when we have 1, 2, 3, like this? Charge 1, charge 2, charge 3. Charge 1 is positive, charge 2 is positive, charge 3 is negative. We want to find the net force on charge number 2. Well, the force on number 2 caused by number 1 is this way. Okay, number 1 pushes number 2 to the right. The force on number 2 caused by number 3 is also this way. Number 3 pulls number 2 to the right. If we wanted to find the force on number 1, well, 1 would be pushed this way by number 2. 1 would be pulled this way by number 3. So if we want to find the force on number 2, get both of these forces, add them up. If you want to find the force on number 1, get both of these forces, add them up. But when you do, make sure that you do what? Make sure that you assign a negative. Make F2 one negative, or as Brendan said, subtract one of them. Basically, it's the same thing, right? Okay. Another real common mistake, guys, if you get a question like this, and these are fairly common to see questions like this. Okay, let's say you're trying to find the force on number 1. You get both of these forces. You add them up and make them both positive. That option will be there. Okay, you're going to see your answer there. Okay, if you make one of those common mistakes that I tell you about, your answer will be there, but it's wrong. So you're going to walk out of the test thinking, oh, I did really, really well, because all of the answers you got were there. Okay, so we've got to be really, really careful that we don't make those common mistakes, because we're not going to know we made them. Okay, if we're not paying attention, we're not going to know we made them until we get our test back. What if we change this to have 3 charges like this? This one's positive, this one's negative, and this one's, let's say this one's positive. 1, 2, and 3. I want to find the net force on number 2 here. Well, number 2 is pulled towards number 3. We're going to say that's F32. Number 1 pushes number 2 away. We're going to call that F12. Calculate both of those forces. Now what do? Add them up? Yeah, add them up, but you got to add them up vectorially. If this was 10, sorry, if this was 3 and this was 4, yeah, I guarantee you, if you had to choose your answers, A, B, C, and D, one of them is going to be 7. Okay, and some of you are going to pick that, right? One of them is going to be 7, but that's wrong. How come? It's not a vectorial or a vector addition. Right? When we add these up, we're going to do the Pythagorean theorem. 3, 4, that equals 5. So the correct answer there would be 5 at whatever angle that worked out to be. And then finally, variable value changing. This is a pretty common place to see the variable value changing, right? That's not crazy hard. But the one thing I'll caution you on, if you do something to the distance down here, r, like let's say we square the distance, sorry, we double the distance. Well, you're not just squaring the r, you're squaring the 2r. Or if we triple the distance, we're squaring the 3 and the r. So let's say it becomes 3r. Well, it becomes, it would be k q1 q2 over 3r squared, which is k q1 q2 over 9 r squared once we put it outside the brackets. So again, talking about common mistakes, if this is a multiple choice question, in this case, the new force would be 1/9 of the original force. If you said 1/3, I guarantee you that option is going to be there, even though it's the wrong answer, okay? This is the one we want there. Yep.
Just for like with the, if we're add up vectorially,
Yeah.
just go over how like if they're calculated that force like 1.
Well, I'll briefly talk about that, but I'd be real surprised if you saw that question. Right, I can tell you tomorrow you won't. If you want to find the net force on number 1, it becomes quite a bit harder because of the angles involved. The net force on number 1 caused by number 2 is this way. F21 is this way, but 3/1 is this way. So you'd have to have an angle there. You may have to find the angle using trigonometry, or you may be given what that angle is. Now, you can find You can still do this, but when you have a funny angle like this, okay, you got to break it up into x and y components, right? We don't like funny angles. So you'd have to kind of draw it off to the side, get an x, get a y, using some trigonometry, and then you have to add up all the x components and add up all the y components, and then get a right angle triangle. Does that make sense? Yeah, I'd be surprised if you saw that. I really would, okay, because the length of that question is pretty long for a multiple choice question. But you know what to do if you do see it. I mean, anything's possible, right? So, good question to ask. Talked about electric fields. There's going to be a question on tomorrow's test. Some of you are going to ask me this. Is it a positive field or a negative field? There's not, like, that question doesn't make any sense. Is it a positive field or a negative field? A field is a field. We define the direction of the electric field as the way that a positive particle would move if placed in the field. But that doesn't make it a positive field or a negative field. Look, if we have a charged particle right here that causes the field to the right of it is to the right. The field to the left of it is to the left. But what if we just have the field drawn? What if we're not told what causes that field? It doesn't matter. If it's a field that points to the right, then we know a positive particle would go which way? To the right. It doesn't matter if we know what caused it or not. If the field points to the right, then a positive particle would go to the right. What about a negative particle? It's going to go to the left, right? Opposite to the direction of the field, regardless of what caused it, regardless of whether it was parallel plates, okay, or a big positive over here, or a big negative over here, or both a big positive and a big negative. It doesn't matter. If the field points to the right, positives go with it, negatives go against it. Remember your diagrams for electric fields. Question number 1 on the test tomorrow, I promise you right now. Question number 1 is a question that just requires you to remember what the diagrams look like. Remember, positive, negative. And it looks something like this, positive and positive, and so on. Okay, those basic electric field diagrams, okay, that we know we're going to have to know for our diploma exam, you're going to have to know for tomorrow as well. Question number 1. That's a gimme question. Okay, we're starting off tomorrow with an easy question. You got to get that right, every single person. We got our 3 equations. You guys know the deal with this, right? Just remember to keep them straight. Top 2 go together, bottom 2 go together. The middle one goes whenever you want, as long as you have an experiencer that feels that field. And finally, the charge distribution. If you have a uniform surface and you have extra charges, where do those charges go? To the outside, yeah, and it's a uniform surface. They're going to go to the outer surface, and they're going to be evenly spaced, yeah. If you have a non-uniform conductor, right, it's a pointy conductor, they're still going to go to the outer surface, but they're going to cluster more in the corners, yeah. They're going to be more concentrated at the pointy parts, whether it's a corner, whether it's a sharp, needle or something like that. We talked about potential energy difference, electric potential difference. Okay, know the difference between those 4 terms. You know the equations. So energy, right? Energy is E. Energy difference is delta E, and that's also equal to W, and that's also equal to F times D. And potential is V, it's E, right? The first one over Q. The energy per unit charge, and the potential difference, of course, is delta E over Q, but it's also equal to VF minus VI. delta anything as final minus initial. Okay, variable value changing could come into play here as well, although it's not as likely as for Coulomb's law. And we talked about the electron volt as a unit for energy. Remember how to convert that? So we have 2.5 electron volts we want to convert to joules, right? 2.5 over x. If we wanted to convert 3.2 times 10 to the minus 19 joules into electron volts, then we put the x on the top. You get a multiple choice question. Electron volts and joules are both pretty common numbers, pretty common units. Okay, joules is what we always have to use, or almost always have to use for calculations. So do those conversions. If you see an answer, okay, pay attention to the units, because sometimes they'll try to trick you with that. You know, the answer will be 425 electron volts. Okay, you get an answer, you calculate your answer that's 425. You calculate your answer in joules. Okay, whatever that works out to be in joules, and you say, oh, okay, my answer's not there. Okay, convert it to electron volts. Or maybe you get 600 joules, let's say. Let's say you get 600 joules, but the answer isn't 600 joules, the answer is 600 electron volts. Okay, pay attention to those units. Okay, not only do we need the right number, you need the right unit as well. And then finally, the last thing that we talked about Thursday, and then we checked over the homework on it today, was the whole conservation of energy thing. Okay, please remember, when a charged particle speeds up, it's like a car going down a hill. When a charged particle slows down, it's like a car going up a hill. EI equals EF.